thank you. Okay, so the point here is to show you how we use some ergodic properties to prove some interesting stuff in number theory. In particular, on the second half, I will focus on multiplicative functions. So let me just say a little bit what is the plan, because it will take a while to arrive to multiplicative functions. So the first thing we'll do is we'll talk about Furstenberg systems. This is actually our way to transfer information from ergodic theory to number theory and vice versa. So I will spend actually half of my talk around this topic. So this is supposed to be an 11 seminar for the experts to take an up. The second part will be this theory's property of strong stationarity. This is a property of ergodic systems. Curious in the sense that you don't find it frequently, but for the purpose of this talk, it will be very relevant. And the third part will be multiplicative functions. I will tell you a few stuff we know about Furstenberg systems of multiplicative functions with an emphasis on spectral properties. Because the spectral properties are going to give me the following corollary. So let's say this will be our to prove this result. I chose this one because it's easier to phrase and easier to prove. I will sketch a proof at the end. So let's say the following result. Consequence. What we'll say here. So if you have any multiplicative function, this is a complex unit disk. For example, if you would like, you can take the Liouville. And if you take any irrational number, and if you look this weighted average, it's where you weight over irrational exponential phases, and the average is always going to go to 0. So you take this limit, you take this average, and this is logarithmic average. I will explain what I mean. We consider correlations to this function. And this is going to be 0 for every multiplicative function. This is true for every L and for every shift N1 and L in Z. Okay, so this is already of interest. Interesting meaning it was not known before. When L is equal to 2 and F is a Liouville function. Okay. But the argument I will give applies to all multiplicative functions. Okay. And actually, as far as I know, there is no other proof other than the one I will show you for this result. Okay. What do we mean by some notation here? Notation about averages. So when I write something like that, I really mean this thing. Okay, when I write this will feature only when we deal with multiplicative functions, the second average. I really mean this average. So we this is weighted average. And some other things that will, so this guy, when I write e to the t, we mean e to the 2 pi I t. Okay. I will need some other. So, okay, we'll explain afterwards what are multiplicative functions with the shape. Okay, so let me just start with the first one, but in order to go to the first one, we need to, first of all, do some crash course in ergodic theory. So I will only mention basic stuff that are of interest for today's talk, okay? Basic measures preserving systems, the list of favorites, my list of favorites. It's different from, depends on the person. But for today's talk, so first of all, let's say we have about measure preserving systems. So the setting is as usual, we have a probability space. And we have a transformation from X to X that is measurable and preserves the measure. Okay. Now, what I'm interested is on a special class of measure preserving system and special properties. So let's say basic properties or favorite properties. Let's start actually first of all with the favorite measure preserving systems. So the first system to look at is rotations. So Px is equal to x plus alpha, let's say on T with Liouville measures. So this system will actually feature frequently. There are simple enough also, or you could take finite cyclic groups or more general groups. The other class that will feature is skew products or affine transformations. Important affine transformation on some finite dimensional torus. So, for example, these are two good examples to keep in mind. This is on T2 with Liouville measure. Or the other guy, which is this one. So if this alpha is irrational, this is what we call ergodic, but there is also this guy that actually does appear frequently. And it has special properties, again, on T2 with Liouville measure. And you can take more levels, higher dimensions. Okay, but these are the two typical examples. And we can continue here on the list. The third type of example, which is a little bit different, nil systems. So either you know what it is or you will know to learn it now. This is G over gamma. This is nil potential group. These are special cases of this. And you have Tx is equal to Ax with the Hall measurement X. Okay. So these are the structural systems, and I don't need anything else. This is the whole class of structural systems I'm interested in. And then we have the random system, which are Bernoulli systems. There are several ways to define this, but the one that is best for this talk is, or let's say, a special Bernoulli system. Let's say if we work in 0, 1 to the Z. This is the sequence space, and you have the shift transformation. So you have a point on the sequence space, and you shift its coordinates. So this is how it's defined. So, and now we have as measure, we take the product measure. let's say the product a half measure, but it could be 1/3, 2/3, whatever. Okay, this is final transformation. This is supposed to model random events. The coin flip, for example, is modeled by this transformation. It has the same statistical behavior. Okay, so these are the first three are considered the structural examples. And the fourth is only random one that we need for this talk. Okay, I'm not clear. Okay, and we have the basic operations also. So for me, something will be on the list of favorite systems, basic systems, if it can be constructed by this one using some basic operations. So for example, I'm allowing to take direct products. Inverse limits. So for example, if we have a rotation on the infinite dimensional torus, can be approximated by its pieces on the projection finite dimensional torus. Factors, subsystems that live inside these systems, and mixtures. So you can take convex combinations of these, or let's say non-ergodic system with ergodic components, one of these lists. These are basic systems, and that's it. Okay, all the systems we want to consider are in this class. I'm not claiming there is a structural result saying that the dual measure preserving system can be constructed by this using this operation. This is very far from the truth, and likely so. Okay, the point is that for natural occurring sequences, all the systems we are going to study are supposed to belong on this list. Perhaps it's very hard to prove, but I don't know of an example of a natural occurring sequence that will give the rise of a Furstenberg system that is not on this list. Depends on the definition of natural. Okay? So these are isolated points in a very complex universe. So we're very happy to say that a system belongs in this list. Okay. This is now the list of favorite systems and some basic properties we want to study. This for today we'll only study these properties. The first one are spectral properties. So when you give me a system, so what is spectral? First of all, what is the spectrum? System. This is a definition. Okay, this is defined to be the alpha in 0, 1. For which there exists a function, let's say, non-zero, such that Tf is equal to e to the alpha f. It's an e to the alpha eigenfunction. Okay, but be careful. So e to the alpha is the eigenvalue. The spectrum I define to be a subset of 0, 1. It's the phase of the eigenfunction. Okay. So this is the spectrum, and we'll say, because this will occur frequently now. So first of all, whenever you have a measure preserving system, 0 is always in the spectrum. Okay. So the spectrum always contains 0. Simply because t of 1 is equal to 1. Okay. But it may contain nothing else. Okay. So trivial spectrum. When I say trivial spectrum, it means that we only have 0. Okay. or a trivial rational spectrum, the intersection of the spectrum with the rationals is only 0. Trivial irrational spectrum, there is nothing irrational. The spectrum stuff like that. Okay, so this is the definition of spectrum. I mentioned this because actually, for example, this property will come out of the fact that Furstenberg systems of multiplicative functions have trivial irrational spectrum. Once you prove this, you get that. Okay. And we have various versions of randomness, ergodicity, measure 3. One way to resist the f is equal to f implies that f is constant. A system is ergodic if it satisfies that. Weak mixing. Df is equal to p to the f implies f is constant. And if alpha is determined 0, it goes to 0. And then the Bernoulli, this is the ultimate sort of randomness, is basically what I gave you, this example. Or this example, okay? Example 4. If you are Bernoulli, you are weak mixing. If you are weak mixing, you are ergodic, but not by that. Okay. So perhaps you have a system you like to prove that it's Bernoulli. It's very hard for Chola. An intermediate question that if you answer, you should feel very happy to prove that it's ergodic, or prove that it's a weak mixing if you can prove that it's ergodic. Okay. These properties, having or not having spectrum, are easy to translate from the ergodic world to the arithmetic world. I can give you pretty much equivalent properties. The Bernoulli properties also easy. This is the Chola property. These two are not so easy. So I can give you the translation, but it wouldn't make a lot of sense. It would be some sort of identities that you wouldn't understand what they mean in the arithmetic world. So this gives you, all that it gives you an advantage in ergodic theory, studying intermediate notions of randomness that would just not occur to you if you work just in number theory. Okay, so these are properties. So basically, when we have a measure preserving system, the basic questions we have is which of these properties it has, and whether we can figure out that it belongs to the favorite list of measure preserving system, and which one exactly. Okay, so this will be our object based talk. And let me tell you now how, given a sequence, how we can construct an ergodic object that actually imitates its statistical behavior. So Furstenberg systems. Let me mention precisely what this means, and then I will put it down there and leave it there. So the goal is given a system, given a sequence, bounded sequence. This is the complex unit disk. Okay, right? You or these. Okay, for me this is the complex unit. Okay. Bounded sequence of complex numbers. Okay, so construct a system, measure system that and a function. This comes with a function. That imitates its statistical behavior. Okay. By this I mean that they have two things have the same correlation, whatever this means, I will tell you now. Okay. This way, when I have a question about the sequence, I could ask an equivalent question about the system, hopefully get some information about the system, and then pass it back to the sequence. That's always the principle. And in order to make so this is always possible, but let me make this precise. So this is the Furstenberg correspondence principle. Okay, so that's a theorem. So Furstenberg used it in the 70s to approximate this theorem on arithmetic progression, but the variant I will give is very useful for the software I'm going to talk about. So you can phrase it as follows. So let me do it like that. So let from the integers 2p be any sequence. Let me phrase it in an easy form first. Then there exists a measure preserving system. E and the function and something else, such that the following holds will have the following identity. Whenever I compute a correlation for the sequence, so let's take our averages here, but it's the same for logarithmic. And here I take a product. Okay, so this is the correlation of the sequence in the arithmetic world. If you are able to compute all these things, then you know pretty much all the statistics that you are going to ask me, the configurations of 0 and 1s, you have complete control about the sequence. Then this is exactly equal with the correlations in the ergodic world, this function f0. Yeah, and the quantifiers here go as follows, that this is true for every L and all shifts. It's not that I change the shifts, I will construct the differences. Let's see if it was here or N. Let's take it from this. Okay. So whenever I want to go and do this computation, I could just go and do the computation in the ergodic theorem. I will find that the same result. So if I want to study these guys, I could just go here and study these guys. If I want to show that these guys are 0 for different shifts, suffice to show that these guys are 0. Okay, so here T and F. Okay. Now, one question, does this formula make sense? Yes?
What statement are you making about the existence of these limits? Is that if
Exactly, so it doesn't quite make sense, so I have to correct a little bit. So if you assume existence of limits and argue for this talk, you can pretty much assume it, then it's a fine formula, but I cannot really assume that these limits exist, and perhaps showing that the limits exist are as hard as showing that the limit is 0. So that's why we phrase it as a subsequential property. So suppose we have a sequence and some subsequence of integers that go to infinity, any. Then there exists a measure preserved system, a function, and the subsequence of this one. Such that this, and here I use this subsequence. So that this property. Now this is a true statement, valid. As I mentioned, this it makes always sense. So you give me any sequence, there is a diagonal argument that allows me to show that I can pass to a subsequence and have all these limits exist. Along this subsequence, I define the system. This is for our purposes, should not bother you because let's say we want to prove Chiala or whatever. Let's say that the problem we want to prove fails, then it will fail along a subsequence. I'll go and work on the subsequence of this for which all these correlations exist. I get a contradiction, hence the original property will be true for the full sequence. Okay, in practice, this is how this works. Should not bother with the fact that we work with subsequence. Okay, this is this. Now, there are several ways of phrasing this. I prefer this one because it just gives you exactly the sort of identities that we use. The thing I want you to remember, I will not erase it actually, is that this is the defining property of the system. Okay, we construct some object in ergodic theory and the function that has this property listed. Yeah, let me make some remarks and then I will give you some examples of Furstenberg systems. So first of all, okay, given a sequence, we call any such system a Furstenberg system of the sequence. Okay, we call let me just write it F system. Otherwise, I will write Furstenberg 100 times today. And the system may well depend, if the limits do not exist, may well depend on the subsequence. Okay, so when perhaps, and it occurs in practice, that you have uncountably many systems, but this should not bother. Okay. The other thing is that I use here, I wrote Cesaro averages. I could use logarithmic instead, and actually this is what I will do for the multiplicative function. No, this, and this could lead to completely different Furstenberg systems. Okay, it's not that this and this have to be somehow related. This take into account what happens towards the end of the interval, this towards the beginning of the interval. Okay. So the systems could be very different. And the other thing, how you construct this, the construction is very simple. So this is a theoretical construction, tells you there exists a system always. And it works on this space with this transformation, the shift. So space is fixed, so the transformation is fixed. That's the shift transformation I mentioned before. The function is fixed. It's evaluation of the zero coordinate. So the only thing that is depends on the sequence is the measure that you put. So the measure, something has to depend on the sequence, and the sub A depends on A and the subsequence NK prime. Okay, so it's all about this measure. Good. Now, what we would like to do in practice is to give us a sequence. We would like to understand this Furstenberg, all possible Furstenberg systems. Okay, this is a fine construction. There exists one, but perhaps we can find a simpler one that does the same job. Preferably one from the list of favorite systems. And this is one of our goals. Okay, this one does this job, but perhaps I can find a rotation on the torus that does the same job. Okay, so the real here. So one of the objectives. So I go in live. So you give me a sequence. first of all, study which of these properties the sequence has. But ultimately, what we would like to do is find the system in this list it's not guaranteed that it will exist, okay? So it would be a nice theorem if you are able to obtain this. That it's isomorphic to this Furstenberg system, so basically that satisfies star. For which star holds. Perhaps there is one, perhaps there is, it's not possible. But in all the examples that I know, it is possible. Natural examples. Okay. System and functional. Okay, so again, I have a sequence, let's say the Liouville function or your favorite sequence. You have a favorite sequence? So can you tell me?
M squared.
Yeah, bounded sequences, okay? You need to have a bounded sequence. Yes, okay, we'll give this. Thank you. You made it easy. So the point is to now go, okay, the first correspondence principle gives you an abstract system. So this is not something we can understand. Perhaps we can find a very simple system, like the rotation of the circle, and the function that does this job. If we're able to find this, then we pretty much know everything about the statistical behavior of the sequence, okay? So let me give you some examples of success where actually we can find the system. It's not always obvious. If the sequence arises dynamically, then it is obvious what you have to do. If not, then you're in trouble. But let's start some examples. I will give you examples of success. Of course, we're not always successful. But the first one, let me do it as follows. So I have a sequence. And I will give you the system. Give me the sequence, I will give you the system. That's the job. The first one is e to the n alpha. Or if you want n alpha mod 1 is the same thing. Fractional part of n alpha, these are the same sequences. Rational or irrational doesn't matter. So the system here is Tx on T, and with a function, I have to give you the function also, okay? And this is the obvious one, f0 of x will be e to the x, e to the 2 pi I x. So if you're going to compute the correlations of this function with this transformation, it will be, it's an easy exercise, you will get exactly this. Actually, this proves actually that the Furstenberg system of when alpha is irrational list is going to be isomorphic with this one. Okay, will be unique correlation exists and isomorphic with this one. We would like to play this game with any other sequence we give. Tell me the next example.
n squared.
Correct. The point here is that Pmx is equal to x plus n. That's why the n alphas arise. So the next example is Txy. You can take 2x plus alpha, it doesn't matter. These two systems are isomorphic. And here, tell me the function. E to the y, correct. We did not plan this, but the stuff. Okay, so, believing you're going to do the computation, you will get exactly the same correlation. So the Furstenberg system of this sequence is exactly this one. Okay, if you want isomorphic, but it does this job.
Do you not need your function to be like 2y plus x or something?
No, it doesn't matter. These are, it will give you exactly the same correlation. So the point here is that if I had x plus alpha, as we say, y plus 2x plus alpha, if this was t to the nth power, you will see x plus n alpha, y plus 2nx plus n square alpha. So you will see exactly n square alpha. This is why the squares arise from this one.
If you do the correlation.
The statement I mentioned about the correlation is correct for this one. Okay. And you put any polynomial, that's same business. Next one.
E bracket and alpha and beta.
Correct. So let's say an alpha and beta. So this will give you nil systems. This is the result of the tal. The point is that all these sequences arise dynamically. That's why it's easy to figure out what should go on the right. The point now is that if I give you a sequence that doesn't arise dynamically, how are you going to figure out the system? So next one. You may try. Another one. Or can you think of a simple system that doesn't arise dynamically? Yeah, this one. I would be impressed.
What if A of n is the first digit of n?
First digit, that was in my list of examples, but later, of which one?
A of n is first digit of n. That was.
Of n. Yeah, but this is too, yeah, that's fine. It's coming later. Okay. So, I mean, you can play this game. It's a fun game. You give a sequence, try to find the system, and very often you have successes. Okay? You get some pleasure points out of it. So we continue with the list. And let's say this one. This definitely doesn't arise dynamically. I don't know if a simple dynamical system where if I compute the nth iterate, I will get this sequence. Okay. It's not very easy to guess, but it's not hard if you think a little bit. Now, if you're going to compute the correlations, you will see you get either 1 or 0, depending on whether some sum is equal to something. So believe me, it's not hard to show that the first number system of this is px is equal to x. It's the identity transformation on t is the vector. And the function here in the obvious one is dx. You compute, the only thing you have to know is that square root of n is equidistributed and sequence that grow like that. So you will get. So this is identity systems. Identity systems have life. They should not be ignored. They don't move a lot, but this one moves and has this as a Furstenberg system. Okay. If you go a little bit further, now it should not be a surprise. This one, and to the 3 halves. Yes, the one that where is it? Anyway, so it will be xy. You don't expect to see x plus alpha, y plus x. I mean, I don't see any alpha here. Okay, so the only likely candidate here, and if this is correct, is this. And indeed, this is it has a unique Furstenberg system. This is it with f0y is equal to e to the y. You can prove this by computing correlations. It's not hard. The correlations on the right are very easy. On the left, using some equidistribution results, you get identities and you prove your result. Okay, and it goes on like that. I can give you other digits. This is interesting also. So let's say first digit. It's like the logarithm. It will not have a Furstenberg system. It will be identities. Let me go to some more interesting one. Go to the I. You've seen this. This is something people have studied. The first digits are not equidistributed. One is more frequent, the Benford law, and stuff like that. So, can you make a guess? It's not. The guess is not obvious. You don't know it.
Stationary system with a non-standard. It's like a bunch of points.
Which in the list of favorite systems is gonna be? If there is one. It's either rotations, skew products, random. Huh?
The doubling map?
It's a fine guess, but it's not correct. Yeah, a priori you may think, but it could very well be a Bernoulli shift, but not a half. On 9 symbols with the different, it could have been. That could have been that, but it's not. It's on the opposite. It's actually a circular rotation. And alpha and alpha, actually this alpha is since I use 2 log with base 10 of 2. The function will not, of course, this is a series that takes values from 1 up to 9. It will be, I would say, a step function. I can give it to you, but I will not now. It's simply to say. Okay. So you get rotations, or if you have, but now you can guess if I say 2 to the n squared, making analogies, you will guess it's thy, and it is correct. These are not hard things to prove, okay? Same out with some function, okay? Or to the and to the 3/2, something like that, and it goes on, okay? Okay, I don't want to give a sense now that you give me a sequence, I can always produce the system, it would be nice. But these are some success stories to give you a sense of what we're really looking for. I want some explicit system. Don't tell me there exists one. Although it's useful, maybe useful just knowing this, but this is much more useful. So for this talk, we're really interested, not trying to prove a general statement about sequences like Semered's theorem. You give me sequence with specific properties, so I want to exhibit a specific system. Tell you as much possible for this one. So before we make a break, let me just tell you some stories where we have actually no clue. You could look on this sequence. If you want the digits, first digit. There is no reason to look on first digit. You can look on middle digit, but things are tougher there. First digit of 2 to the 2 to the n. Or if you want digits of whatever number, square root of 2, pi, e, nothing is known about this, okay? No, I mean, when I say nothing, no non-trivial property is known. Of course, for all this, it is expected that the Furstenberg systems are Bernoulli. But even proving that it's not a trivial system, that it doesn't have irrational spectrum or anything, if you are able to prove anything like that, you should take pride to yourself and let me know, okay? Nothing non-trivial about this system. It could be anything. Okay, so things could be very tough, like stuff, but for multiplicative functions, you can say a lot of things. And that's the point. We can say a lot of stuff. There is a lot that we know, a lot that we don't know. Interesting stuff. For example, we can at least show that the Furstenberg system of any multiplicative function will be on the list of favorites. Okay. Perhaps there is one, perhaps there are several, but they are all going to be on the list of reference. Belong to. But this is not something that I will prove now. I will prove something else.
What is it from Mobius?
So, yeah, and here is the catch now. Although I can tell you that it's on the list of favorites, I cannot tell you which is which. So if you give me Liouville, I expect to be Bernoulli, Mobius, Bernoulli times and inverse limits of rational rotations, but I cannot prove it. The only thing, so the exact statement just said before is that the ergodic components are direct products of nil systems and Bernoulli systems. This is something we've proved with Bernard. But I will not talk about this result because it's more complicated. And the statement is already. It's not, I cannot translate it back to number theory. Now, the other thing that I mentioned somewhere, the correlation property can be translated to absence of irrational spectrum. And so I will focus on this, okay? Okay, let's have a 5 minutes break. And we'll move on. The strong stationarity and then okay, so should continue. So let me say a few words about this strange notion of strong stationarity. And then I will see how I will apply this to get. So the way actually to show that systems of multiplicative functions do not have irrational spectrum is by showing that they have a variant of the property that I will mention here. Okay, it's a trick. If you know it, fine. If you don't, it's not something you will think about. So there is a general notion that applies to abstract measure preserving system. Let me just mention it for sequence-based systems. Let me mention as a property of sequences, okay, which is more relevant for our topic. This was a notion introduced by Furstenberg and Katznelson in the early 90s. They were trying to prove the density Hales-Jewett theorem, and they managed to show if they prove it in the strongly stationary setting, then it holds in general. So it helped them for their purposes. It will help us now for something different. Okay, so we say this is the definition one. It's not the optimal one, but good enough for us. We say that the Furstenberg system this is the Furstenberg system and always comes attached with a function. Let's close it like that of the sequence. So this I'm talking about this system, okay? And it comes attached also with the subsequence, okay? Is strongly stationary. And let's call this SST. If it satisfies the following curious dilation invariant property, basically what I will say that these correlations remain invariant if you substitute, if you multiply everything by R. Okay, it's a curious property. If, let me write it in the ergodic terminology first. This F0 is equal to and the quantifiers go as follows. This holds for every L and N1 and L in Z. Yes, so which reminds me, in all this discussion, because we also use functions that have complex value, when I want this identity to be true, I allow also, if I want in some positions to put complex conjugates, then I allow this, and here I should put complex conjugate. Okay, actually I apply this identity in this setting when I compute correlation. Okay, so I would like this identity to be true with F0 or F0 bar in various different places. And if you put on the left, you put on the right.
Maybe to in some instances, but not in others. So
Yeah. You may use half zeros and half of them, which frequency you have to if you want to get cancellation, if you want to get non-trivial correlation. This is what we do. Okay.
But you assume this for every choice of.
For all choices. This identity holds for. Now, be careful though that F0 is the specific function which is evaluation of the zero coordinate. I'm not allowed to use this identity for all functions, just for F0. If you want in the arithmetic universe, this is a fine property to discuss about sequences. It tells you this. A sequence that has its statistics satisfy this curious property. This is easy to calculate. That's it. Okay. So, for example, I will just go to a couple of sequences in the example. If I have to see which kind of sequences have this property, the Furstenberg sequence or do not have. If you have this sequence and you go here, you compute even the 2-point correlations, you put F0, F0 bar, then the outcome will be, over here will be n e to the n alpha. You have cancellation. But if you substitute e to the n alpha, e to the Rn alpha, then they are not the same. So this one is not strongly stationary. It's very simple, like computing correlations to show. The Furstenberg system will not be strongly stationary. This is the same thing in the ergodic world if you have Tx is equal to x plus alpha, because basically, let me just write. If I compute An and plus, let's say just 1 and plus r, this is with complex conjugate, then this is you just plug inside this e to the r alpha, which is not equal to e to the alpha for every r. Okay, so you definitely don't want to see rotations inside your system, and you definitely don't want to see. It's not a proof; it's hard to prove. But if you are going to see eigenfunctions in your system is very likely not going to be strongly stationary. And actually, that's a theorem. Okay? If I go the same thing, if I go to the n square alpha, this is not strongly stationary. And this is not if alpha is 0, 1, it's not 0. But if you go to n to the let me write now a fact. That's a theorem. Djembe is a mathematical brother of mine. He was also a student of Katznelson before my time, who proved the following very nice thing. If you have a strong stationarity plus ergodicity, if you have a system that is simultaneously ergodic and strongly stationary, then it has to be Bernoulli. It's not a real fact of life, but it's true. So this is a very strong property to have. Within the class of ergodic systems, you will only find only one candidate, Bernoulli system. It would have been an excellent result and would have made life much easier if, in general, strongly stationary systems were mixtures of Bernoulli. Then we would have probably proved Cauda and all these nice things, but it's not a true fact of life, unfortunately. So if you go to the non-ergodic case, there are several strongly stationary systems I will mention. in words, but I will not give a proof. First, you have to go and prove that you don't have eigenfunctions. I will show you how you don't have irrational eigenfunctions. Once you have this, you get weak mixing. Once you get weak mixing and this property, you average over R, you use Furstenberg's weak mixing result. That's first one, correct? And it goes to the product, hence you have Bernoulli. So the key point is to prove no eigenfunction. Okay?
Sorry.
Tell me.
I was going to ask, so you gave this definition for Furstenberg systems, but it seems that there is a definition of strong stationarity.
Yeah, for systems. There is, yes, but then I want to, so a system is strongly stationary if you have a degenerating algebra of functions, so these are the F-zeros, which obey this identity. Degenerating meaning the subalgebra spanned by this and iterates is the full system. Okay, so this is what I mean, really, to make sense of it.
So there exists a generating.
There exists, yeah, over here, for example, you may try the e to the y, it will not work, but there is none because it's a theorem. Okay, so yes, things that are strongly stationary in the ergodic case, here it is. So in the non-ergodic case, this actually sequence, that's why I mentioned it before, or the square root of n's. With Lebesgue measure, it's important to take Lebesgue measure. All these are strongly stationary. I mean, you can go over here. If you compute the correlations, you will see that it's either 0 or 1 if you have ni's, or the same with r times ni. It's a difference between when you have it. So these are non-trivial examples of strongly stationary systems, but they have to be non-ergodic. Okay. And this gives us, of course, trouble. But in any case, exhibiting strong stationarity is an interesting property. It gives you stuff, it will not give you Bernoulli. But here is a theorem that I will actually use. Okay. A strongly stationary system, let's say, with this definition, does not have a rational spectrum. So let me just tell you how we prove this quickly. Convince you at least. The same is true with rational spectrum also, but this will not be relevant for us. And this is a strange way for us to prove that something does not have a rational spectrum without going and computing correlation, because this is what we cannot do. So the key point is you want to show that something is 0, and without computing a single correlation, you just manage to show that the correlations are kind of dilation invariant, and this will give you that you don't have a rational spectrum. It's a strange way of proving it. Actually, this can be rephrased as an elementary statement, but I don't know how to prove it without passing through ergodic theory. You have a sequence, satisfies this identity, show that it has this weighted Joule property. Perhaps there is a way to do it. It would have been nice to see a way to do it elementarily with avoiding ergodic theory. But the proof goes through non-existence of an eigenfunction, which is really an inventory object. It's hard to translate this in the arithmetic universe, so I cannot translate it. So how does this go? And it is a fact that in the non-ergodic case, you can prove this is something I did in the past. Ergodic component of strong systems are nil systems times Bernoulli systems, from the impulses of nil systems times Bernoulli. So we have a structural result for this. So strongly stationary systems belong in the class of favorite systems. Okay?
Even without elements.
Ah?
Oh, okay.
Okay. So proof, sketch of proof. The proof is kind of elementary and nice, but it has a couple of prerequisites which are easy. The So let's say that chi is an eigenfunction. Okay, so what is the goal? We have Tx. I do not know by chi the eigenfunction is e to the alpha. Chi and alpha is irrational. Then I will show that chi is equal to. Okay, this is equivalent. I'm showing that I don't have a rational spectrum. Now, step one is an observation, but it's a useful one. The point is that this is now an identity about correlation. So I would much rather have extract some information about some operators from this. Some maps would be much more useful for me. And here it is. So there exists. This is just an observation. Maps tau are from X to X that satisfy the following properties. First of all, there are three properties. T tau r is equal to tau r T. Okay. Second is are measure preserved, very important. But let me put this first. X6, the function of 0 that I have here. And the third is that PR are measure preserved. They preserve the measure mu that I have. Now, the proof of this is simple because these tau are maps are basically dilations. These maps are very explicit. So I'm on the sequence space. I had the shift. Now I define a new family of maps. This is always fine. You easily show that this is satisfied, always without assumptions. This is also satisfied. The zero coordinate is not going to change. So the point where we use the assumption of strong stationarity is this. This is pretty much a restatement of strong stationarity. The fact that these guys are measure preserved. This is so the last property is important. Okay, it's equivalent to strong stationarity. Good.
It's true in general for ergodic system. If you start with an ergodic system that doesn't come from the Furstenberg construction, can you show the existence of these maps?
Yes. Okay. Yes. But yes. So step two, let's see what happens to eigenfunctions when we hit them with these guys again. Elementary exercise, believe me, you can do it if you try, not now. So TRX, because basically if you go this function, if you use the commutation relation, T to the R of this will remain invariant, hence it's going to be a linear combination of if lambda is this, lambda 1 over R eigenfunction. Let's call this lambda. And it's linear combo. Where lambda is equal to e to the alpha. So basically e to the alpha over R modulo roots of n. Okay. This is something very easy to get. And let's now go to step 3, which is the important. So we want to show that this is 0. In order to show that this is 0, it suffices to show that chi, in order to show that chi is equal to 0, that it's orthogonal to a T-generating algebra. So it suffices to show that integral chi Pj F0 d is equal to 0 for all choices of L and J. If we show this, this is with F0 and conjugates also. Okay, if we show this, we will be fine. We will accept that chi is equal to 0. So let me show you how you do this for L is equal to 1 and 2. So quickly, so let's say that we want to show that F chi F0 is equal to 0. Let's start with this. To show that it's orthogonal to F0. Okay, then what you will do, you will fit it with tau r, you have nothing else you can do. So this will give you tau r chi, tau r leaves f0 invariant, and it is measure preserving. So I use two properties times f0, give me. And this holds for every r. Now, these tau r of x are eigenfunctions associated with different eigenvalues. You use that alpha is irrational. So they have to be pairwise orthogonal. These alpha over r's are different. So this tau r of x is going to converge weakly to 0, hence this is going to be 0. So if you take limits here, because tau r x pairwise orthogonal, we use that alpha is irrational here. It's going to go to 0. This was equal to this for every r, hence this is 0. Okay, it's not as easy later, but let me just tell you. For L2, if you see that two, the general case is very similar. Okay, so what you want to show is that let's say TF. So let me just put this. It doesn't matter if I put to the K or conjugate. So again, I will do the same trick. It worked so nicely, so why not? Again, I use measure preserving, commutation relations. I use all the properties basically. And I get that this is equal to this for every r. Now, problem. This converges weakly to 0, but this depends on r. Perhaps this also weakly converges to 0 and they cancel out. So I cannot really, say something. But what we do in this area, we want to show that something goes to 0. What do? We take averages, correct? So this is going to be equal to this. Hence, and we know how we cancel guys like that. We use van der Korkut. So in order to show that this is 0, so suffices, so apply this twice actually. You need one time already here, so it's twice here. Suffices to show. I tell you the final result. Believe me, you do the computation, something simple. So suffice to show that for all ST large enough, when you average over R, TR plus S T tau R plus T. This looks like the Gauss dot, but this will not exist at that point. So you put complex conjugates. Suffice to show that this average is equal to 0. Now, the important thing is that I have cancelled the F0s and only have information about the Chi's. And this guy, if you call it Chi RST, is actually going to be, if you compute it down, it's here you have A over R plus S, A over R plus eigenvalues. So if you take linear combinations, they will never cancel because alpha is irrational. So in a different argument when it's irrational. These are going to be non-trivial eigenfunctions, meaning eigenfunctions not for the eigenvalue 1. Hence, all of them will actually have integral 0. Okay, hence you will get this. Here you use the alpha. So this is a rather simple argument. There is not really something more to it. But it goes through the non-existence of an eigenfunction. How you translate this now into the finitistic world if you want to do something, I don't know. Okay, so we're going to use this. Questions?
Well, you use algorithm. Oh, you didn't.
No, I don't. And actually, I do not want to use algorithms. Here, I show that the general struggle spectral system is not going to have a rational spectrum. And this is how I want it for the multiplicative functions, because I definitely do not know that they are ergodic, okay? I don't use ergodicity here. Afterwards, when you saw absence of a rational and irrational spectrum, use ergodicity to say that it's a weak mixture. Okay. Now, for multiplicative functions, have some examples. Would be very brief. Just idea. So now the multiplicative functions, a lot of them do have a rational spectrum. You take Dirichlet characters, this will give you a periodic system. You take a multiplicative function that is on some prime minus 1 and all the other primes 1, it will have spectrum 1 over p to the k. It will be a procyclic system. So a rational spectrum you have a lot. What you are not allowed to have is irrational spectrum. The Mobius has a rational spectrum because its square is a square-free number. So a lot of rational spectrum that the Liouville is not supposed to. So this is the theorem. So usual definition. You have to see probably multiplicative just this. Then it's Furstenberg systems do not have irrational. Yeah, this is something to do with so, by the way, it's a question, and it's a very interesting one. About a rational spectrum, I told you that a lot of them do have. Does a Liouville function, of course, you expect answer no, okay? Rational spectrum. Non-trivial. For example, show that a half is not in the spectrum would be very will have very interesting consequences also. And this is far from proving the Chawla conjecture. A sequence could be very well not have a half in the spectrum, be very far from a random, could be a rotation on 3 elements. Okay, so it's consistent with reality to be able to prove something like that without proving Chawla. Okay, but we don't know how. Would like to prove this. So how do you prove this? If you have this theorem, has as a consequence the application dimension false. There is something that I forgot. When I say Furstenberg system, I should always say what kind of averaging I take. And for this, I have to say for log average. You will see, I don't know this procedure. Because on the very starting point, I will do something that is on for okay. So it will imply that that I wrote in the beginning. Okay, so basically, because if this was false, then you would exhibit a non-trivial joint between this and an irrational rotation, but this cannot happen. Or more elementarily, if you Vanderkorp this relation and use the spectral theorem, you will get it. The definition is the exercise. Okay. So if you have this, you get that. Now, how do you prove? Let me just say here. Tell you the first step and then quickly why this property at least makes sense. On the very first step, we need some input about how we're going to use the we have a Furstenberg system of a multiplicative function. We need some properties for our measure preserved system to get started with. Let me give you the identity for f is equal to lambda, but a more complicated argument works for every f. Okay, so using Tau's identities, this is an identity that some of you saw in the first semester by Teravine and how you use the entropy decrement argument to get some interesting identities for German sequences. And if you apply them for multiplicative functions, they will give you identities for multiplicative functions. If you translate them to ergodic theory, they will give you what I will write now. So this implies that if x is the Furstenberg system of my multiplicative function, this is lambda now, and f0 is as before, then here's what you get. F0 is equal, so this correlation is equal to the average derivative correlation. I average over primes here. Integrals, and I use the Furstenberg system now for logarithmic average because this is only when I'm allowed to use the identities of Tau, only for logarithmic averages. Okay. So here it is. This is the one. The truth is you have to put -1 to the L, but there is a trick to get rid of it, forget about it. If you have modular multiplicative functions, there are some CP here that create trouble. Anyway, let's stick with this formula. Okay, so this is a very curious formula. This is very special measure preserving systems that have this property. It's not very easy to find a measure preserving system that has this property for F0 some t-generated function and is not the Bernoulli system, for example. Perhaps, if life was good, we would conclude from this that the system is Bernoulli, and then we would have a Chala, but it's not, it doesn't work like that. Okay, so but at least from this identity, we will show that the system has no irrational spectrum. Any system that satisfies this property for some t-generated function F0, this is for all nj. This is true for all L, and necessarily will not have irrational. It could have rational. And the way we'll do this is we will actually exhibit. It's not really that we will prove from this that the system is strongly stationary. This is a false statement, but it has some strong stationarity feature. So step 2, so let me just make a reduction to see the idea why. So let's assume that T was totally ergodic, or let's say that T had a trivial rational spectrum. Let's just assume to see what we get. Suppose this is something that we cannot prove. But let's suppose. Remember, we want to prove something for the irrational spectrum. I'm not assuming something about the irrational to conclude, but I'm assuming something about the rational. Then here's what happens. So when you go and you compute these things, so this identity holds for all nj. So in particular, I can apply it for Rnj in place of nj. And I will get that this is equal to the average p integral pj is equal to 1 up to L R p nj. Correct? Then just apply this identity for this dilate. Now, if your system didn't have a rational spectrum, say is totally ergodic. Then let's say it was a rotation, you know, you go here, you do computations and you have P and J times alpha for alpha irrational is going to be equidistributed, but it's the same thing if you had R alpha. It will give you the same computations, at least for irrational rotations. In general, it's something tougher to prove, but you will get that this thing, this limit is the same as the same limit without it. I will tell you a bit what is involved here. There is some work, okay? And this would be equal again at length, right? And if you compare these two, you would get a strong stationarity. Hence, no rational spectrum. One moment. This is here. Okay. Now there is a lot of, but this is ergodic work involved here, but likely it was done in the past for us. A lot of stuff. Oskara, Ziegler for formulas, Green-Tau, Ziegler, inverse Gaussian important of the modified von Mangold. All these things are used here, or you could get it with a little bit less, but you have to use some stuff to do these computations.
Is that
okay?
That equality or the next one?
To show that this is equal to this. Look, I had here an average with some iterates, and I was able to average over the primes, and I was able to replace it by the dilates, by multiplied by R. If you have a rational spectrum, this is impossible. This is a false identity. The fact that you don't have a rational spectrum, your T is totally ergodic, do it for rotations. Makes this identity true for rotations, and it's true in general. This one. The others follow from the definition, from the defining property. Okay. Now, let me just tell you, of course, proving that the system has trivial rational spectrum, this is actually what we originally tried, but it's still an open problem, that the Furstenberg system of the Liouville has trivial rational spectrum.
If you prove that, you essentially prove that they are binary.
No, I just proved this dilation invariant. So it's consistent with reality that for the Liouville function, the system is x, y plus x. This is a strong extension system. It satisfies this identity. And it could be that the Liouville function is isomorphic. It would be very strange, unexpected, but people have tried and failed. Okay, so it doesn't prove that, unfortunately, because there are these guys or higher levels. So how we get now the point is that we can prove stuff like that without making this assumption, which is still open. So here I will hide a lot of stuff, but I have to do something. So we can reduce, so now I will not tell you how, because that's a different story with work, okay? It's not an exercise. To the case, but this is a true statement, where, okay, we cannot say that the system has trivial rational spectrum, but it has finite rational spectrum. This is basically because nil systems have finite rational spectrum. After we prove that ergodic components are direct product of nils times Bernoulli, property that I told you is true for all multiplicative functions, we will get this. So these things have to go together. I cannot avoid the big step that I will not describe here. So what happens if you have this? This basically means that if you have a system with finite rational spectrum, you take some d power and you clear denominators, and you get that the x mu t to the d has trivial rational spectrum, meaning ergodic components are total. Doesn't mean ergodic. It means ergodic components totally ergodic.
now it has no rational spectrum.
This qualifies also. This qualifies also. Okay. And once you have that, then you're just going to, so you have this weaker assumption. If you're going to repeat this argument, then this limit formula, you have to substitute something, you will get the same limit formula, star, it's the same computations, star false when R, I will not get for every R, that's all. I will get it when R belongs to DZ plus 1. Believe me, it's computations. Yeah. Okay. Which is not as strong as strong stationarity. We don't call it a weak strong stationarity. We will have straight or partial strong stationarity. But this is enough. I mean, if you're going to repeat GMP's argument with just this dilets, it works fine. Okay. No reference.
It's not true that the Liouville would have finite rational space.
No. The story of how we reduce here is unfortunately complicated. And I don't have a way to phrase it and explain it without going into this system of arithmetic progressions that makes things easier for me. Cannot rephrase all these things inside the system. A true statement, we never wrote it, should be of the following form. The Liouville system of any multiplicative function is a factor, important because I have to go to the system of arithmetic progressions, is a factor of a system whose ergodic components is a factor of a system that is a mixture of systems that can be approximated by partially strongly stationary systems. So go figure out. In any case, so whatever property we get is enough for. There is an ergodic decomposition at some point. That's okay. So with this, I would like to close. The main point is you have interesting things to prove. You want to prove interesting things about correlations of a sequence, translate them to ergodic theory, and try to figure out whether you have some of the favorite properties, whether it's on the favorite list of systems that would be nice, or this strong stationarity. This is also a favorite property to search for. If you have it, you get interesting stuff. Okay, thank you.
Any more
Questions?
Yeah, very quickly. I was confused as to how the structure theory stuff came into the equal sign. You put a circle around
Here, no. At some point, in order to do computations, I have to replace the primes, let's say, with the integers.
Okay.
For example, so when I say this, I mean the Gauss uniformity of the modified von Mangold function. So once you have this allows you to replace primes with integers, because at the end you have to do some computation here with nil systems, and I wouldn't like to have primes.
But how do you reduce the case of Hill systems? Is that because of
Oh, so the story goes as follows. So for this, we have character already. Tammy has found at some point characteristic factors of these things that they are nil systems. Alternatively, for primes, it's also true. You can either use just a piece of the original article, arithmetic progressions on primes, and do some work, more ergodic work. Or if you want to avoid it, you use a Gauss uniform of the modified von Mangold, and you compare it with averages over the integers, for which there are two ways, depending on how much number theory you want to use. Yes, so characteristic factors for these guys likely are known. If they were not known, no, it's there are alternates, but I have to know something. Yes, it would have been, my life would have been much tougher. Okay. But for this kind of argument, I don't actually even need to prove, let's say, that the Liouville has average 0. I don't need stuff like that. Or something about the only number theory input is here, or something that allows me to compute this for nothing else. Okay.
So this fact you stated here that strong stationarity plus ergodicity implies Bernoulli reminds me of your older result that if you know the Furstenberg system for the Liouville is ergodic, then you get shown.
Yes, yes.
Is there a other connection there? Or it's just...
Yes, when I proved this, which actually I had no idea about this stuff. Perhaps one could give an alternate, at least in the total ergodic case, one could give an alternate proof of this using this subsequent stuff. It wouldn't cover the functionality of this result, but for the Liouville, it would give this. But I had to get full strong stationarity. That's the thing. Okay. So that's why if I assume total ergodicity, I would get it. Without it, I'm not sure if this would simplify.
Hi, I have a question. Great talk. Do you know anything more than you knew in your annals paper with Host about any Furstenberg system of Liouville? The fact of Bernoulli times, I guess, inverse limit of mill system, yeah. That's your structural theory. Do you know anything further since then?
Unfortunately, yeah, for the Liouville, I mean, we're looking with Marius and friends about other multiplicative functions, but for the Liouville,
let's stick to Liouville, yeah.
Liouville, no, nothing very interesting that I can say that is not already covered there. For example, so there are two main problems. One, disqualify this possibility, which we know it's related to the local quadratic uniformity of Liouville, and people work on that, but this still has not been disqualified. And the other is the thing about the rational spectrum. I'm very interested on this, but even shown that a half is not on the spectrum of the Liouville. Not yet.
Okay.
And if anybody is interested, I welcome some help. Okay.
Yeah.
No.
That's why we brought you all together.
Yes.
We're supposed to solve this.
Yeah. Yes. Get something new.
Fantastic. Okay, thanks. Yeah, sorry I couldn't come. I don't come in the morning, but anyway, I got some bug here. You don't want to see me.
Very quickly, is there a combinatorial statement that would be equivalent to this in the spectrum of Liouville? Is that is there a sort of concrete combinatorial statement you can make about that's equivalent to saying half is not in the spectrum of the...
Yes. For all alphas, yeah, these are very the things about the spectrum. They're sort of equivalent, at least the certain line. So it's a very interesting, easy thing to write. Let's say logarithmic to make life easier. You need something to get started. -1 to the n. This is a half. Morally. Certainly this implies.
So for non-logarithmic, this would be hopeless. But,
okay, we don't have a starting point, but why you really want the logarithmic? To prove it here, and we're happy. Okay, you want to get arbitrary long ones on the range of the Liouville? Prove this, and you will get them. I guess if you prove this, you will prove it for all values in the spectrum. Okay. So one may think, oh, this is very close to Chala, but it's not. If you could be a rotation on 3 elements and satisfy this property. It's not a notion of randomness having this property for all correlation. Just a little bit half is not in the. If you are a system, you don't have a half in the spectrum. It could be anything in your life. It's a weaker property. Much weaker than Chala.
Particularly,
if you want, if you average on even and odd, you get the same average. Without being able to compute any of this, I just want to know that the difference between odd and even is the same. That's what this tells you. Make sense? Something else?
over lunch, maybe?
Yes, okay.